So there we go. Okay, so scale factor, we want to talk a little bit more about that today, just to make sure we're okay. And then we're going to look at scale factor in relationship to area and perimeter of shapes as well. So we're going to see how the scale factor affects areas and perimeters as well. Okay. Okay. This is what I want. So when a shape is dilated, okay, its sides change by a number called the scale factor, right? Okay. And remember, the scale factor, right, is the way we find that. And I'll zoom in on that. So I'm sorry, I realize it's kind of. There we go. Okay. The scale factor is the ratio of the what over the what? Yes, be careful. Image over pre-image. I'm going to keep reminding us about that over and over again because I want to make sure it's like we've got that down. So image over pre-image. Now, we have a variable that we use to kind of like denote the scale factor. And what I mean by that is, for example, we know the variable m, right, the letter m, we typically use that in algebra to represent like the slope of something, right? Or like the letter b in algebra is used to represent the y-intercept, especially when we're talking about lines, okay? Well, in scale factors, okay, we use the variable k to describe the scale factor, okay? So for whatever reason, k, okay, is the variable or letter we use whenever we say the scale factor of something. Okay. It's actually, interesting, like the pi is actually a letter that we use to represent the number 3.1415926. I don't know if you guys realize that or not. Pi is not a number. Pi is a letter of the Greek alphabet. So if you guys ever go to like a college campus or something like that, the fraternities name themselves using Greek letters, normally like 3 of them, and pi is one of those Greek letters you might see. Okay. Typically, though, the pi on like a fraternity or sorority has like a straight top and then the 2 things, whereas we draw the pi kind of with a curly, kind of cute like that. But that's pi. So what's that? So that's more one you'll see in math, but this is the one you'll see when you see like you'll see like I don't know like see like theta pi alpha or something like that. I know, like, that's their Greek letters, and that's their name of their fraternity. GTA. Right, yeah, it kind of looks like that, doesn't it? Yeah, actually, so the theta is supposed to be like that, but it's supposed to be like a full oval there. That is funny. But yeah, I think pi is like a p sound, and alpha is like an a, basically, and then theta, I think, is like a th. I'm not sure, though. Anyway, it's very interesting. It's hard to read. And actually, if you ever look at Russian, too, the Russian alphabet incorporates, like, Greek letters and, like, English letters, and it's, like, really, and, like, weird other letters, too, and stuff like that. It's crazy to look at. Anyway, so k, though, like I said, is our variable for scale factor. So let's just do an example here. So, for example, all right, let's find the scale factor of the dilation below. Okay, so And okay. Okay. So there's our picture. Okay. And again, we want to find the scale factor. Remember, we call the scale factor K. Okay. So find the scale factor K of the dilation below. So there's our dilation. All right. So remember, scale factor, right, is image over original. So Justin, what would be our ratio here that we want to set up to find that scale factor? What over what could we say?
34 over 17.
There you go. Perfect. 34 over 17. Justin, what's another way we could have found the scale factor here?
4 over 2.
Yep, 4 over 2. Yep, and that's pretty much.
Even if the free image is larger than the freeware image, we're still doing image over free.
Yes, exactly right. Because that will indicate to us the type of dilation it is. I'll show you here in a second. So K equals 34 over 17. Now, do you know what that simplifies to?
1/2. Or
2. There you go. Yeah, 2 over 1. Very good. Or just 2. Same thing here, right? 4 over 2 is 2 over 1, which it should be the same thing because they're from the same kind of dilation there. That's right. Okay. Very good. So if we look here, right, our... Wait a minute. I did this backwards. I apologize. Image over pre-image, right? So what's the measurement from the image, Justin?
The image, yeah, 34.
How do you know this is the image?
Because the other one is prime. That's the
No, the primes means it's been transformed. So this is the image. That's the original. Image has the primes. Original does not have primes.
So, image is the original. Or no, pre-image is the original.
Pre-image is the original. I know, and I agree that is the dumbest thing that I think it's the dumbest thing I teach you guys in geometry, that we call the original the pre-image.
Let's just say prime over original. How about that?
Right, so prime over original, that's fine. So 17 over 34 is what it should have been there. Okay, which is then 1 over 2. Nope, that was my mistake. I let it go. So equals then 1 over 2. Okay, sorry. That was the point. Because again, why does this 1/2 scale factor kind of make sense here? What's happening to our from our original to our image? What's happening?
Multiplying, or it's like increasing in size by half.
So it's decreasing. Okay, it gets smaller. That's how when I looked here, Justin, I was like, wait a minute, 2 over 1. That means our original should get bigger when we go to dilated, but that's not what happened. So I knew we had it wrong. It needs to flip, and that's something you guys can do too. When you look at your scale factors, okay, if your scale factor is bigger than 1, your dilation better be bigger than the original. If your scale factor is less than 1, your dilation better be smaller than the original. If it's not happening that way, you need to, correct that, okay? Because there's what it should be. Okay. So, in summary, right, if the scale factor is greater than 1, okay, what happens to the shape? Shape gets bigger. Yeah, we talked about it, but now we're writing it down officially. We've talked about it, but I don't think we actually officially talked about it. So, and then also, if the scale factor is less than 1, the shape gets smaller. Right, and if it is 1, then the shape stays the same. Exactly right. All right, questions on any of that? All good? Okay. Question, yes. Oh, okay.
Alright, so...
Is it all right, go ahead.
Alright, so you know me about here. Yeah. Is that because your brain is making electric currents, or is it
description.
No.
This is like a science question.
Yeah, so, because your hair, so I mean, yeah, obviously, yes, your body does operate on some, like, does have, like, electricity, like, kind of, like, you know, going, a current through it, I guess I want to say, right? That's your nerves and stuff have a little electricity firing through it. But I don't think your hair is a good conductor. Like, I don't think you could, like, attach, you know, a wire to one end of your hair and a wire to the other end of your hair, and I don't think electricity would pass through it. So, yeah, it's what Jay is saying there. It has to do with, like, the electrons and stuff like that.
That was such a weird question.
And that's why we look.
Yeah.
What's that?
That's right. Opposites attract. We can look more at that here after we're done the notes.
It's a no bomb.
Find the scale factor. Let's do a little more here. We're almost done. I don't have too much more for us here. I just want to look at now the scale factors, perimeters, and areas. So we'll look at one more problem, one more situation, but we're going to kind of look at it pretty in depth here. So find the scale factor of, and here I'm going to name it in a different kind of way. Rather than giving you a shape and then its image, like the primes, I'm going to write it out like this. So I want us to find the scale factor of A, B, C, D, 2, E, F, G, H. Now, in that naming, I'm not really making it clear or obvious. Maybe I am, some of you. But which one of those is the original? Which one of those is the image? Which one of these two is the original? Which one is the image?
The A, B, C, D is the original, yeah.
And E, F, G, H, you're saying is the image?
Yeah, because you put that one first. I'm just guessing.
Okay, you just put, because I put her first?
Letters at the beginning of the alphabet, it starts.
Okay, fair enough.
Yeah, I mean, you don't have the, like, the shape, so I don't know.
ABC is the original.
Yep.
Yeah.
You could
He's
do
right.
this and say the other one could be original.
I could, but I think, and I believe we're going to go with this as a class, because I think this is right. The idea is that A, B, C, D, okay, is going to E, F, G, H, if that makes sense, right? A, B, C, D to E, F, G, H, and so that to me indicates that this is like the original, and we're dilating it to E, F, G, H.
Yeah, they just saw, like, that was, you had that first thing.
Well, maybe you did like subconsciously, right? You at least had an intuition that this was the original and this was the image, so that's pretty good still, okay? So good intuition there. All right, so let's draw a picture here of A, B, C, D, and E, F, G, H. So let's see. I'm going to draw another rectangle here. Kind of boring, I know. These rectangles. Someone's like, Mr. Witt, it's not the rectangles that are boring. It's like, well, thanks. Nice. Okay. Well, they didn't say it. They were just thinking it, I'm sure. That's okay. Okay. And we'll draw another rectangle. Uh-huh. That's right. Talking about dilations. And we'll say 6 and 18. That's okay. This is not art class. This is geometry class.
No, I mean, like, with just the shape of it, like, it's bad.
That's okay. It's okay. Just label it accurately. That's what's important. That's okay. Just label it appropriately. You should be fine. Okay.
So wait, are we going to do the ratio thing?
So, right, the directions say find the scale factor of this shape. So let's go to Austin. Wiki, eggs and bakey, okay? So Austin, scale factor here, K equals. And by the way, Austin, I did not call on you on purpose because I saw your head down. It literally just had your number there. But it was good coincidence. Anywho, so remember, scale factor is image over original. We just established with Chris that and Quante and a few other people that ABCD was the original, EFGH is the image. So give me a measurement from the image. Just pick one. You can't see? Give me a. Well, now I've really made it easy too. But go ahead. Give me a measurement from the image. 6. And we'll put that over what's corresponding to the 6 here. 4. Yep, there it is. Yes. Okay, so image over original, and that simplifies to 3/2. For those of you that aren't sure how to simplify your fractions, if you have a graphing calculator, if you type in 6/4 and then hit math, enter, it will convert it to a fraction simplified for you there, 3/2. Or you could have done 18 over 12 as well, and you do the same thing. I'll show you here. 18 over 12, math, enter, enter. It's also 3/2 when you simplify it. You see that there? So, yep, you have your choice. You have your choice there. Okay, there's our scale factor, which again, shouldn't surprise us, right? If we're saying this is the original and this is the image, 3/2, is 3/2 bigger than 1 or smaller than 1?
Smaller.
3 divided by 2 is 1.5. It's bigger than 1. So that's why our shape got bigger. Okay, makes sense. All right, let's now find the scale factor of the perimeters.
Wait, they equal the, or they equal the same, but we was just to set up, I got both, I got the same thing.
Yeah, they're supposed to be the same, yeah.
Oh, you are? But
Yeah.
they got bigger, how would it be like that?
The same scale factor.
Oh.
So they both got bigger by the same
Oh, see, that's how you
amount.
know that they're similar. So, yeah,
Yes, yes, exactly right. Okay. All right, so we have to remember how to find perimeter of something. Let's see here. So, Bryce, how do you find the perimeter of a shape? What do you do?
The length times width times height.
That is the volume
Oh, there you
of
go.
something. How do you find the perimeter, Jay?
3 times length, what's 3 times length?
Yeah, for a rectangle, you can just do twice the length, twice the width. It's adding up all the sides of the shape. And so in this case, we have a 12 here as well as a 4 here, right? Rectangles, the opposite sides are congruent. And so the perimeter of ABCD then is 12 plus 12, 24, plus 4 plus 4, so that's going to be 32. Okay. Likewise, the perimeter for EFGH is going to be 18 plus 18, so 36, plus 6 plus 6, which is then 48. And so then the ratio here of our perimeters, E-Shep, is going to be what over what? I already wrote the perimeters out for you, so which one's going to go on top?
48 over 32.
You got it. Very good. Now, those are two big numbers, but they do simplify, right? So 48 divided by 32, math, enter, enter. Look at that. 3/2. Where do we see that 3/2? That's the scale factor of our sides.
So we're learning how that we're using the perimeters to find the same thing.
So what it looks like is that the scale factor for the sides is the exact same scale factor as the perimeters. So if you wanted to, you wouldn't need.
The perimeters to find the scale factor.
Yes. Or you can use the scale. You can use the scale factor to find the perimeters. If you know the perimeter of one shape, you can then use the scale factor to set up a ratio.
How do you find the perimeters?
The perimeter of a shape. So the word perimeter, right? If you think about it this way, like whenever you're telling someone to guard the perimeter or something like that, they're supposed to guard the outside of the place. It'd be like a fort or a building or something like that. So when you're talking about the perimeter of a shape, you find the distance around the outside of the shape. So you add up all the sides.
Oh.
That's what it is. Okay. All right. Last relationship I want to look at is I want to find the scale factor of the areas.
Yes, we can that too. Actually, I think
I was going to say, for rectangle folks, that's we should know that. No problem. But if you don't, well, now you do.
it's been a while since we covered this kind of stuff, like area of perimeter.
Okay. Area, that's right. All right, so we're going to find the scale factor of the areas of ABCD to EFGH. So you guys already said basically how to find the areas there. We're going to multiply length times width. And so let's see, the area of this rectangle is going to be what times what?
What, ABC?
For ABCD,
12 times 4.
12 times 4, so that's going to be 48. Yep. And then the area of this rectangle is 6 times 18. I think it's 108? Yes, 108. Okay. And then the scale factor then, remember, that's the original, that's the image. And so our scale factor is image over original. So what would that fraction be then? What over what here? What do you say there, Carrie? 108 over 48, you got it. Now, this fraction simplifies. Is it going to simplify to 3/2? Math, enter, enter. 9/4. Interesting.
Wait, so it's not supposed to be the same as the other one?
It's not the same as the other ones.
Wait, won't it simplify to it? Or no?
9/4, that's as far as it simplifies.
Oh, wait, yeah.
Right? You can't divide
You can't divide 4
by 3.
and then-
Or 9 divided by 2. That's right. But, does anyone see a relationship here between our other scale factors and 9/4?
I have no idea.
Jay sees it. What is it, Jay? Oh, let's get someone else a shot. Sorry, I want to give someone else a shot. Go ahead, Lamel, what do you want to say?
Being one thing multiply those two, you get that.
3/2 times 3/2? Okay, Seth, what do you want to say?
I was going to say something along those lines. I was going to say that the denominator is a multiple of 2 and the numerator is a multiple of 3.
Yeah. So 9/4. Jay, what do you want to say? Okay. So, yeah, our scale factors here, okay, the scale factor for the sides, the scale factor for the perimeter is the same. The scale factor for the area is the square of those scale factors. If you take 3/2 and you square that fraction, you guys remember what does it mean to square something? Multiply it by itself. So 3/2 times 3/2 is 9/4. And that's going to be true in general, okay? The area scale factor. This is it, and I'll give you guys the assignment here. The area scale factor, okay, equals the square of the side, okay, or perimeter scale factor. Okay, talking two-dimensionally there. If we were talking in 3 dimensions, so if we had like a cube or a rectangular prism, okay, and if we had a rectangular prism that was similar to another rectangular prism, okay, the side lengths of those similar rectangular prisms would have a certain ratio. The area of a face would be the square of that ratio, and then how would the volumes be related of similar rectangular prisms? What would you do? If you square it for the area, what would you do for the volume? What would make sense? If you square the scale factor for the area, what would you do for the volume scale factor?
Google search how to do it.
Google search how to do it? That's an answer. You could do that. All right, well, I'll let you guys think about that then.